In section 10.5, we're going to start talking about scientific notation. The first thing I want you to do, though, is do you know what happens on a standard calculator when you multiply two big numbers together? For example, let's say you took 2 billion by 3 billion on a calculator, and you got something on the screen that looks like this. 6.0, and then there might be an E, and then plus 18. What do you think that means? Because I know if you've taken a basic calculator and you've multiplied really big numbers, you might get an error. Doesn't mean you can't do it, but you might get an error, or you might get something that looks like this. So we're going to start talking about standard notation and scientific notation. Now, standard notation is when you take just a regular old number, like 5,780. That is in standard notation. It's just a plain old standard number. Now, in scientific notation, it would look something like this. Now, if you don't know how we got that, that's okay. But I want you to understand the difference of identifying something in standard notation, which is just a normal number, and scientific notation, which looks like this. So let's go over our key idea. Here's what our key idea looks like. Now, scientific notation. Today we're just going to read things in scientific notation. Scientific notation is a number that is represented by a product of a factor and a power of 10. So I'll say that again. A number is written in scientific notation when it is represented as the product of a factor and a power of 10. That means we are multiplying a factor times itself by 10, and then the power tells us how many times we're doing that. Now here's the most important thing, is students will make mistakes on this. It's here in the green. The factor must be greater than or equal to 1. This number right here. Greater than or equal to 1, but less than 10. Once it gets to 10, it actually is going to go back to 1. And you'll understand that as we look at some examples. Now this is the power of 10. The power of 10 has an integer exponent, so we're always going to have an integer exponent. Now I'm hoping you realize that if you take a number and multiply it by 10, let's say 7. 7 times 10. That gives you 70. Now 7 times 100, if I wrote it as a power of 10, we could say 10 squared. 7 times 100 gives us 700. Now I know your multiplication facts. I know you understand this. But I'm more concerned that you understand what happens when you multiply by 10. So if you did 7 times 10 to the third power, that means you're going to multiply what? What would you multiply 7 by? It'd be 1,000. So this would be 7,000. Now what happens every time? Every time you multiply by 10, what happened? Now if you said that you added a 0, technically that's correct. But if you did this, 6.83 times 10, that gives me 68.3. I didn't add a 0. 6.83 times 100, or I'm going to write it as 10 squared. That gives me 683. What's happening? I'm hoping that you realize that every time you multiply by 10, the decimal place moves over one value for every 10 that you multiply by. So the decimal moves over 1. Here we multiply by 100, so the decimal moved over 2. In our first example, we're just going to identify whether or not the number is written in scientific notation. So example 1, tell whether the number is written in scientific notation, and then I want you to explain. So in part A, we have 5 and 9/10, 5.9, times 10 to the power of negative 6. Is this written in scientific notation? The answer is yes. It is, because the factor, which in this case is 5.9, is greater than 1 and less than 10, and the power of 10 is an integer exponent. So let's look at b. Would b be written in scientific notation? 0.9 times 10 to the 8th power. And your answer would be no, because 0.9 is less than 1, therefore, because the factor is less than 1, it is not written in scientific notation. So now we know what standard form and what scientific notation is. But now, we're going to write numbers that are written in scientific notation, we're going to write them in standard form. Here's how you do it. The absolute value of the exponent indicates how many places to move the decimal point. If the exponent is negative, you're going to move the decimal point to the left. If the exponent is positive, you're going to move the decimal point to the right. So for example, 5.321 times 10 to the 6th power. Now, if you really wanted to, you could take 10 to the 6th power, figure out what number that is, and then multiply it by 5.321. The problem is if you have a basic calculator, your calculator is going to give you an error message, or it's going to give you your answer in scientific notation. So all you do is we look here at the exponent, and in this case it's positive, so it's 6. That means we're going to multiply by 10 6 times, and every time you multiply by 10, the decimal goes 1 to the right. So we're going to move the decimal 6 places to the right. So we're going to take 5.321, 1, 2, 3, 4, 5, 6. In the 6 spaces, 3 of them have a number. The other 3, there's no number, so we add zeros. So your answer is going to be 5,321,000. If I gave you 7 times 10 to the negative 2, because now the exponent is negative, we're going to move our decimal to the left 2 spaces. So our decimal place is to the right since it's the whole number, so we're going to move it to the left 2. And my answer would be 7/100ths, or 0. Let me change that here. 0.07. Now, I'm hoping you remember from negative exponents that when you're multiplying by 10 to the negative 2, that's really taking 7 and timesing it by 1 over 100. So basically, all you're doing is dividing by 10 twice, or you're taking 7 divided by 100. And that would be 7/100ths, which also gives you 0.07. So let's do some examples, more examples. Example 2, write each number in standard form. So if you already know what you're doing, pause the video and do it yourself. Otherwise, in part A, 3.22 times 10 to the negative 4, since we have a negative exponent, we're going to take our decimal and move it 4 spaces to the left. My decimal then is here. I add 3 zeros. So my answer would be 0.000322. In the second example, I'm going to take 7.9. Since my integer exponent is positive, I'm going to take my decimal and move it 5 spaces to the right. So since I already have one number, that means I'm going to add 4 zeros. So 790,000 would be my answer. In example 3, this is on page 439. Example 3, an object with a lesser density than water will float. An object with a greater density than water will sink. Use each given density in kilograms per cubic meter to explain what happens when you place a brick and an apple in water. So the first thing we have to do is compare each answer. So we're going to take them and write them as numbers in standard form. So water. Water, I'm going to take 1 times 10 to the 3rd. So I move the decimal over 3. That means in water, it would be 1,000 kilograms per cubic meter. The brick, if I move my decimal over 3 spaces, would be 1,840 kilograms. And the apple If I move it over 2, it would be 641 kilograms. Well, the water is 1,000. That means which ones are going to sink and which ones are going to float. Well, the brick will sink since it's greater than 1,000. And the apple will float since it is less dense than water. So because the apple is less dense than water, it will float. The brick is denser than water, therefore it will sink. In example 4, a dog has 100 female fleas. How much blood do the fleas consume each day? So how many female fleas do we have? We have 100. If we look at our picture here, each female flea consumes about 1.4 times 10 to the negative 5 liter of bloods per day. So what would you do if this is for one flea and we have 100 fleas? Well, you'd multiply by 100. You'd take 100 times 1.4 times 10 to the negative 5th power, which would be 100 times, we're going to take our decimal, move it 5 to the left, which would give us 0.000014. So if we multiply that, we are going to get 0.0014 or 14 ten-thousandths. So the fleas would consume about 0.0014 liter or 1.4 milliliters of blood per day. And actually, that's kind of disgusting to think about that.